so what we were talking about the other day is that gases were special. We can do work with them. We can do work with them because they can expand to fill their container, and they can expand because they form very few to no IMFs with one another. And so we can predict how gases behave using some basic laws. And we were starting to talk about 4 laws. We were talking about Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. And today we're going to throw in a 5th one called the ideal gas law. All right? The ideal gas is just all of these combined into one, and then they throw in an extra variable in there that deals with the number of particles that are in the container. All right, so Boyle's law and Charles' law we discussed already. Boyle's law and Charles' law are laws where you think about a certain number of molecules of a gas in a flexible container like a balloon. Gay-Lussac's law is a certain number of particles in a rigid container. So something like a glass box, or if you want to think about something more practical, like a piston in an engine. A piston is basically a canister made out of metal. So that does not allow volume to change. And so what we were talking about the other day is that on the test, what I'm going to expect for you to be able to do is to state the law, give me the equation. So that means that you might have to memorize these equations, explain why these things happen, and then be able to do some math. So let's just review real quick Boyle's law. So Boyle's law is something that's observed when temperature is kept constant and when the number of particles that you're studying is also kept constant. So the example that I gave in class was 5 particles in a balloon. Say those 5 particles are in a balloon that occupies a volume of 1 liter. And those particles are buzzing around and hitting the walls of that container with a certain amount of force. If you were to measure that force, perhaps it would read, the pressure sensor would read 1 atmosphere. All right, what happens if I take those 5 particles and put them in a smaller balloon? Perhaps a balloon that's half the volume, so half a liter. Well, the pressure would increase. And the reason why it would increase is because those particles now have a shorter distance to travel before they find a wall to collide against it. And so you're going to get more, you're going to have a chance that you're going to have more particles hitting the walls of the container, so you're going to increase the number of collisions with the container. When you increase the number of collisions, they're not necessarily going to hit with any more force. The only way that you get more force is to make them move faster. And the way that you get things to move faster is to give them temperature. So they're not going to hit with more force, but they're going to hit more frequently. That's going to give you an increase in pressure. All right? Now, that relationship between volume and pressure is an inverse relationship. All right? And Boyle's law can be summarized with this equation here. V1 times P1 equals V2 times P2. So if the volume goes down by a factor of 2, the pressure is going to increase by a factor of 2. It's really straightforward. We did a sample problem. We did sample problem 14.1 on page 457, and it seemed like everybody had relative ease doing these types of questions. So then we moved on to Charles' law. All right, so let's review Charles' law again. Charles' law is another set of laws that came from observations in the laboratory. And the experiments that were done here, pressure was kept constant, number of particles was kept constant. Tiana, I'm teaching and you're in my class now. Dude, no you're not. Joey, I'm not playing. Okay? All right, so if you have a volume of 1 liter, so the same 5 particles in a volume of 1 liter, and that balloon's kept at 25 degrees Celsius, and then you heat up that balloon. We all know that the balloon is going to expand, right? But the question is, by how much? So some people would say, okay, well, that temperature triples, so I expect the volume to triple. All right, well, that's a problem. Because when you actually go and do this experiment, the volume doesn't really triple. It only goes up from 1 liter to 1.17 liters. Okay, so why? Well, first of all, we need to understand why the balloon expands. So at higher temperatures, what occurs is that the particles over here on the left-hand side start moving faster. They have more kinetic energy, and they start pushing against the walls of the container away from each other and expanding. All right? the relationship is direct. So when the temperature goes up, the volume goes up. All right, but why is this not threefold increase? All right, that has to do with the equation itself for Boyle's law. So I'm sorry, Charles' law. Charles's law is V1 over T1 equals V2 over T2. All right. Well, here's the problem when it comes to using this equation. Temperature cannot be in Celsius. It has to be converted to Kelvin. And then the way that you change temperatures from Celsius to Kelvin is that you add 273. And year after year, when students fail this test, not a whole lot of them do, because this is pretty easy math. The reason why students do poorly is because they forget to do this. All right, they forget to convert to Kelvin. You have to convert to Kelvin. The reason why you do it is because reaching 0 in Kelvin is almost impossible. So you'll never have a temperature that will be 0. However, reaching 0 Celsius is really easy to do. I can go in my freezer and experience 0 degrees. All right, well, we have to avoid zeros, because if you substitute in a 0 temperature for one of these denominators, you end up with an undefined function, and then you won't be able to do any math. All right? So that's why we change it to Kelvin. All right, so if you change the temperatures in the prior example to Kelvin, and I'll go back to the picture so you can see it. So 25 plus 273 is 298. 75 plus 273 is 348. You'll notice that 348 is not 3 times 298. Right? So if the temperature in Kelvin doesn't triple, we can't expect the volume to triple. All right, so how did you get 1.17? You substitute into this equation. So my initial volume was 1 liter. My initial temperature was 298 Kelvin. The final volume, I don't know. The final temperature is 348 Kelvin. So to solve for V2, you cross multiply. So you do 1 times 348, which is 348, is equal to 298 times V2, right? So 298 V2. And then to get V by itself, you would divide both sides by 298. The final volume is 1.17 liters. All right? Questions? All right, let's go on and do, let me show you Gay-Lussac. All right, so Gay-Lussac is a little different from Boyle's and Charles in that in this case, we are thinking about gases in rigid containers. And we're looking to see what they do in a rigid container. All right, so for this relationship that I'm going to show you to work, the volume is kept constant. That's why we're using a rigid container. We're using a container that can't expand and contract so that we can keep the volume the same. So what kind of a container am I talking about? I'm talking about like an aerosol can, right? It's made of metal. It can't get bigger. It can't get smaller. Talking about a piston in an engine. The volume cannot change. It's made of metal. It's too dense. All right? Exactly, that's how it works. The number of particles, again, is being kept constant. And so, again, you'll notice that my picture only has 5 dots in it. All right? All right, so say, for instance, we have this case here on the left-hand side. So I've got 5 particles in a metal can. All right? Those particles have a certain amount of kinetic energy. They're buzzing around. They're hitting the walls of the container. And that can is at room temperature, 25 degrees Celsius. And say that I'm capable of measuring those collisions, both the number of times those particles collide with the wall and how hard they do it. And my sensor basically tells me that that pressure is equivalent to 1 atmosphere. What would happen if I heated up that can to 75 degrees? Well, what are the particles doing? You're right. They're going faster. They have more kinetic energy. They hit the walls of the container more frequently. And they're also going to hit it with greater force, right? Okay, so the particles collide more frequently and with greater force. And then what happens to the pressure? It increases, all right? So you might think, all right, well, this looks like this is 3 times, this final temperature is 3 times the original temperature. So maybe you would expect the pressure to also be 3 times the initial pressure, but the truth of the matter is that it isn't. Why not? Exactly. Well, the relationship is direct again, so when the temperature goes up, the pressure goes up. But the problem is that here's the equation for Gay-Lussac. And I'll zoom back so you can see the whole thing. So P1 over T1 equals P2 over T2. It looks an awful lot like Charles's law, right? What did we have to do to temperature in Charles's law? Change it to Kelvin to avoid a zero in the denominator. Guess what we're going to have to do here in Gay-Lussac? The same thing. Your temperature has to be in Kelvin. So if you change those temperatures to Kelvin, then it's no longer a tripling. And I didn't even bother showing you the work in the substitution because these were the exact same values I used in the prior example, right? The only difference is that now I'm just getting a different unit. It's going to be in atmospheres, not liters, that I'm solving for. So I don't really want to show you how to do this again because it's just a repeat of what we already did and we had in our notes. Okay? All right, so what I want to do is take a moment and do sample problem 14.3 on page 461 for you. Okay? All right, so 14.3 on 461. Let me move things around here and zoom in so you can see it. All right, so it says, aerosol cans carry label warnings not to incinerate the cans or store them above a certain temperature. All right, so who would be so stupid as to put a can in a fire? Okay, you don't have to raise your hands. That was kind of a rhetorical question. All right, so are you a good igniter? They are good igniters, right? People who live in big cities might want to worry about this. So if you live in New York City and you live in a big apartment building with a couple hundred other people, you don't throw all your trash in the garbage and put the bags outside. Because on garbage day, you would have a big mountain of garbage bags in front of your building. So a lot of these large, high-density living type of situations, a lot of those buildings will have incinerators in the basement. So you take your garbage to the incinerator, you burn the combustible stuff, like leftover food, paper products, and those kinds of things. You burn it. And then whatever's left, like aerosol cans, those then go in the garbage bag. That goes to your landfill. All right? You wouldn't want to make the mistake of throwing a can of Aquanet in the garbage, right, and take that garbage to the incinerator. Why not? It would blow up. There goes your building. All right? So you want to be careful about these things. All right? This is not an example for a book that is a trivial thing. All right? So the question asks, the gas used in an aerosol can is at a pressure of 103 kilopascal at 25 degrees Celsius. If the can is thrown onto a fire, what will the pressure be when the temperature reaches 928 degrees Celsius? All right, so let me grab a fresh piece of paper here. What I do is I go through the question and I just start to write down. I jot down what are they telling me. So they tell me a pressure of 103 kilopascal. And then they tell me a temperature of 25 degrees Celsius. All right, well, what do I know about Celsius? Can I use Celsius for these problems? No, it's no good. So I go ahead and I write plus 273 just to remind myself it's got to be in Kelvin. So I go ahead and do that conversion as I'm making an inventory of the information that I'm given. All right. Then they say the temperature is going to shift to 928 degrees Celsius. And again, that's not a unit that I would like to see. So I'm just going to add 273. Ooh, that's big, isn't it? How much is it? So 1,201 Kelvin. Okay, notice it's not degree Kelvin, it's just Kelvin. All right? Oops, get that out of the way. All right? Okay, so now I write down the equation. P1 over T1 equals P2 over T2 for Gay-Lussac. And, okay, so some students at this point just go ahead and substitute and solve for the thing they don't have. You could do that. Some people like to isolate the variable you don't have and then substitute. Whatever works is fine. All right, so let me substitute in for P1. So P1's 103 kilopascal. T1 is 298 Kelvin. P2 is the variable I need. T2 is 1,201 Kelvin. All right, so to solve here, you cross multiply. So you end up with 298 P2 is equal to, we cross multiply over here, 103 times 1201. And then to get P2 by itself, then we divide both sides by 298. All right, so whatever answer I get out of my calculator, I have to make sure that it is rounded to the same number of sig figs as the input that you put into this equation that had the fewest sig figs. So we're going to do 102 times 1201 divided by 298. All right, so what do I get? I got 415. What are the units? You always have to give a unit. KPA. There's no 0.1. Well, let me just double check. Yeah, no, that you can't. The least sig figs here would be this value or that value, and that only has 3 sig figs. So you have to round it to 3 sig figs. It's least sig figs, not most. All right. But don't forget KPA. Well, how did I know it was KPA and not atmospheres? Well, you go back and you see what pressure. What were the units for pressure that they gave you? You want to stay consistent. Okay. All right. So to recap, we've got Boyle's law. The formula is P1 V1 equals P2 over V2. We have Charles' law. It's V1 over T1 equals V2 over T2. We have Gay-Lussac's law, which is P1 V1 over T1 equals, oh, I'm sorry, no. Give me the wrong one. It's P1 over T1 equals P2 over T2. All right? What you need to worry about while you're doing your homework and while you're doing the test is not necessarily the equations per se, but knowing when to use which one. All right? So I'm gonna give you some tips as to know, so that for you to figure out when do I use Boyle's, when do I use Charles, when do I use Gay-Lussac. All right. Okay. Well, how do I know when to use Boyle's? Well, if they ever in the question tell you that the temperature is constant, or they give 2 P's or 2 V's and they ask for P or V, right? Then that's when you know to use Boyle's law. Okay. How about Charles's law? Well, with Charles's law, the way that you would know to use this equation is that somewhere in the word problem they're going to tell you that pressure is constant. Or the other way that you would know that you have to use that equation specifically is that they would give you 2 V's or 2 T's, and then they would ask for V or T. And then finally, with Gay-Lussac, the way that you would know whether you had to use this particular equation in the word problem is that they would tell you that volume is constant, or you would see somewhere in the word problem 2 P's or 2 T's, and they would ask for P or T. Okay? Two P or 2V, and they would ask for P or V. Okay? All right, now there is one equation where they take all 3 and combine it into one. Has a great, fabulous name. Really hard to figure out how they came up with this. It's called the combined gas law. Right? I don't know. They were really imaginative with this one. The combined gas law is P1 V1 over T1 equals P2 V2 over T2. I'm not necessarily going to show you how to do one of these, because it's the same stuff over and over again. You make an inventory of all the things that they give you, and you solve for the variable you don't have. How do you know you have to use this equation over the other ones? All right, well, for this one, somewhere in the word problem, you'll see 5 givens. All right? And they won't tell you that anything's being kept constant. So if you have 5 given somewhere, you can count off 5 numbers somewhere in that word problem, you go straight to this one. Okay? All right. So I'm going to show you one last equation, and we're done for the day. So the rest of the period you can use to do problems. And what I'm going to encourage you to do is come and check my answer key so that we can figure out whether you're doing them right or wrong. Okay? All right, so this next one, which is the final one, is called the ideal gas law. The ideal gas law is essentially all of these combined, but then they factor in one more thing. They factor in the number of particles that you have. All right, so in all the pictures that I drew for you for Boyles, Charles, and Gay-Lussac, we kept the number of particles the same, right? With the ideal gas law, now we're going to start looking at, well, what happens if instead of 5 dots in the balloon, I have 20? Will pressure be different? Sure, because now you have more particles hitting the walls of the container. Well, what if I now have 20 particles and I also change the volume and temperature? What happens to pressure? Or what if I have 20 particles and I change pressure and volume? What happens to temperature? It shouldn't hurt. It's easy. All right? Okay, so we're going to go with the last equation now, and it's called the ideal gas law. All right, so the ideal gas law is great because that's really the only equation I memorize. The ideal gas law is PV equals nRT. And I'm not going to explain what N and R are just yet. I'm going to talk to you guys first about how you can use the ideal gas law to derive all the other equations. All right? This is the master equation. How can I derive Charles's law from the ideal gas law? Well, what does Charles deal with? Volume and temperature, right? Is that true? One way to remember this is Charles is from Vermont. Come up with a stupid mnemonic device to remember this. All right, so if you look at the equation PV equals nRT, right? The first thing that I do is I get rid of everything but V and T in this equation, right? So I get rid of the P, I get rid of the N, and I get rid of the R. Remember all those equations were reflexive, right? So the left side looks like the right side, but what we put on the left are the initial values, what we put on the right are the final values. How do I get V and T together on the left of the equal sign? What would I do mathematically? Divide by what? By T, right? Because we're ignoring the P, we're ignoring the R and the N. How do you get V and T together on the left? Divide by T, right? Oh, look, there's Charles's law. V over T equals V over T. All right? All right, what about Gay-Lussac? Gay-Lussac. That looks at temperature and pressure. Gay-Lussac, he went and TP'd his teacher's house, right? All right, look at the ideal gas law. PV equals nRT. So ignore everything but pressure and temperature. How do you get P and T both together on the left of the equal sign? What would I do? Divide by T. If you divide by T, what do you end up with? P over T equals P over T. Oh, look, there's the equation. I didn't have to memorize it. What about Boyle? Boyle was VP of the senior class. You see what I did there? It's called a mnemonic device. It helps you memorize things, right? So let's ignore everything but volume and pressure. How do you get volume and pressure together on the left of the equal sign? They're already there. Look at that. How convenient. PV equals PV. If you memorize the ideal gas law, you don't have to memorize any of the other ones because you can derive them. All right?
Okay, so this is just figuring out which equation it is?
Well, no, it's I'm just trying to show you don't have to memorize them. You can figure them out from the ideal gas law. So if I ever decided to be a jerk and not give you a formula sheet, and you still need to know the formulas, you could figure it out. Okay. All right. So let's talk about the ideal gas law. PV equals nRT. Well, how do I know when to use this question? All right. So remember Boyle's, Charles, and Gay-Lussac. You know to use them because one of them will tell you the temperature's constant, or the pressure's constant, or the volume's constant. And then combined gas, you know to use it because they give you 5 givens in the word problem. All right. The ideal gas law. You know to use this equation. This is your go-to equation. If ever in the question they give you moles or grams, or they ask for moles or grams. All right? So if they give you moles or grams, or they ask for moles or grams, just start off with the ideal gas law. All right? Write that down. This is important. Because next week sometime I'm going to give you a bunch of problems. I'm not going to tell you if it's a Charles, Boyle, Gay-Lussac ideal gas. They're going to be mixed up, and you're going to have to figure out what equation do I use, when do I use it, when is it appropriate. It says give moles or grams, or ask for moles or grams. All right, so let's take a look here. Well, what's P? All right, that's pressure, but the ideal gas law is really finicky. You can't put any old unit for pressure. It has to be pressure in atmospheres. So you have to know how to do those conversions. All right? What about V? Volume. All right, so again, it's very finicky. You can't put any old volume unit in here. The volume has to be in liters. All right, what's T stand for? Temperature. Has to be in Kelvin. There's 2 new letters here that you're not familiar with. All right, so the first one's N. Okay, so what does N stand for? N is the number of moles of substance or gas that you're dealing with. All right, so N is the number of moles of gas. All right? And then R is a special number. R is called the ideal gas constant. And you want to write down what I'm going to show you. What I'm going to show you is different from the way the book teaches it. I do not want you to do it the way the book teaches it. All right? It's not stupid. It's just that they use a totally different value for R. It's in a different unit. And they do that to get you ready for physics. This is the only book that I've ever seen in my entire career that does it this way. Every other chemistry textbook does it the way I'm going to show you. All right? So R is a number you memorize. All right? It's 0.0821. And the unit for R is liter times atmospheres over moles times Kelvin. It's a number that's actually measured in the lab. All right? And it's the reason why this equation is so finicky, why the pressure has to be in atmospheres, the volumes in liter, and the temperatures in Kelvin. Because when you put everything in this equation, you want those units to cancel out with these units. All right? And that's how things were measured in the lab anyways. They were measured in atmospheres, liters, moles, and Kelvin, because those are SI units for those variables. All right? So I'm going to show you 2 sample problems, and then we are done. All right? You guys done copying this down? Okay, great. All right, so I want to do sample problem 14.4 in your book. Actually, no, I lie. 14.5. 14.4 was a combined gas law question. So 14.5. 14.5 is on page 465. Okay, so let's read it together. All right, so it says, at 34 degrees Celsius, the pressure inside a nitrogen-filled tennis ball with a volume of 0.148 liters is 212 kilopascal. How many moles of nitrogen gas are in the tennis ball? All right, so there's my big old red flag. How many moles? They're asking for moles. what's my go-to equation? Ideal gas law. So I know that that's what I'm going to be using. So I'm going to go back and I'm going to start making a list of everything that they tell me. So I know I have to use PV equals nRT. All right, next. They tell me a temperature. The temperature is 34 degrees. What's the problem with that?
It's Celsius.
It's Celsius. It should be Kelvin. So go ahead. Take the time at this particular point to convert it to Kelvin. All right, so 273 plus 34 is 307 Kelvin. All right, next. Then they give me the volume. The volume is 0.148 liters. Is this an appropriate unit for the ideal gas law? Yeah, we're good. All right, next, pressure. They tell me the pressure is 212 kilopascal. Is that okay? No, it's bad. I want to change that to atmospheres. Well, how do you change this to atmospheres? For every 1 atmosphere, there are 101.3 kilopascal. So 212 divided by 101.3 is 2.09 atmospheres. All right, they were asking for moles, so that means that I'm going to try to see if I can solve for N. All right, well, there's one last thing missing. What is that? R. What is R? It's a number you memorize. How much is it? 0.0821. All right, so I write my equation, PV equals nRT, and I'm a fan of isolating the variable that you don't have and then substituting. All right, so how would you get N by itself in this equation? So N is equal to PV over RT. All right, now substitute. So the pressure is 2.09, the volume is 0.148, R is 0.0821, and then your temperature is 307. And then you take all those things and you pop them in your calculator, right? So I get an answer, right? It's a long answer, lots of decimal places. What do I write down? How many sig figs is the least accurate input? 3. So how would you round that to 3 sig figs? Oh, look at the next door neighbor. It's 227. So what would that be? 0.0123? Okay, so it's 0.0123, and then I was solving for N, right? What's N? Moles. So that would be moles of what? What gas? It's a tennis ball filled with nitrogen. So it's that many moles of nitrogen. All right? If they had asked for how many grams of nitrogen, what would I do at this stage? You multiply by the molar mass off the periodic table to convert to grams. All right? All right. Questions? Let's do 14.6. It's on the following page. Actually, no, I don't want to do 14.6. I want to do question number 29 below it. The reason why I don't want to do 14.6 is because they use some fun. They're asking for some funky units. All right, so look at this question. It asks, what volume will 12 grams of oxygen gas occupy at 25 grams and a pressure of 52.7 kilopascal? All right, great. If they give you grams or moles, or they ask for grams or moles, what equation do I use? Ideal. So again, we're going to start with identifying the equation that I'm going to use as PV equals nRT. All right, so then they tell me that I've got 12 grams of O2. How do I feel about the gram? I don't like it one bit, right? So what would I rather see? Moles. 1 mole of oxygen has what kind of a mass? How much is it? No. 32. Why 32 and not 16? It's diatomic, right? Okay, so 12 divided by 32 is 0.375 moles of oxygen. Okay, next. Then they tell me the temperature is 25 degrees Celsius. What's the problem there? I'd rather see Kelvin, right? So how much is that in Kelvin? That's 298 Kelvin. All right, and then they tell me the pressure is 52.7 kilopascal. Okay, what's wrong with that? It's not an atmosphere, so how do I change it to atmosphere? 1 atmosphere is equal to 101.3 kPa, so let's go ahead and do that conversion. 52.7 divided by 101.3, I get 0.520 atmosphere. They want volume. They don't know it. All right. About the only thing that I have left to put on my little inventory here is R. Right? I know R. R is a number that I memorized. It's 0.0821. So then at this stage of the game, you have everything ready to substitute into the formula. Right? I'll do it over here on the right-hand side. So I know, and actually, again, I'm a fan of isolating the thing you don't have first. How do you get V by itself? V is equal to? How do you isolate V? nRT divided by P. Okay, now I can shove numbers in. All right, so N is 0.375. R is 0.0821. T is 298. P is 0.520. I get an answer. How many sig figs do I round that answer to? I like this ridiculous answer, actually. That's a ridiculous answer. Hang on. Did I forget a decimal?
Yeah.
0.375. Let me try again. That makes a little bit more sense. I get something like this. How do you round that to 3 sig figs? 17.6. All right, what is the unit for that? You always have to give a unit. Well, it was volume. It's got to be in liters. Okay? All right, so that's basically it. And so now you have the rest of the period to work on some problems. And the problems that you need to work on are on the board, but I'll write it up here so you can see. It is page, is it 480 over there? Page 480. Numbers 54 to 58, 60 to 61. All right? So go ahead and get that done, and then I'm going to come around and check.